Hi everyone, good evening. Thank you for staying for one of the latest sessions. I'm Natalia from Cerebras Systems, and today I will share with you some of our pains and learnings from training large-scale models. I don't know how many of you know about Cerebras. We are a company that builds our own hardware, but we also train models, and we are lucky because we have access to very large amounts of compute, so we can train large-scale models, and we learn a lot from doing that. And I'm proud to say that kind of all of the models we've trained, many of them are open sourced, are quite of high quality, especially if you compare that to the models of the same size out there. So as many of you know, when you start your journey on training a model, your aspiration is that you will see this nice loss curve which goes down steadily, and everything is nice. In reality, unfortunately, it's not so simple. So usually, even before you start seeing any loss at all, you often run into things like out-of-memory errors or distribution errors, especially if you need to distribute your models across multiple devices. And even when you are done with all of those errors and finally some losses are coming down, your model frequently diverges. It's unstable, it's tricky. And even when you get over that, quite frequently you are not where you want to be. Let's say you got a paper published, you expect your model to be of that quality, but as a result, it's not quite there. And the reality is training those large-scale models is not as easy. It's a very large number of parameters. Talking about large language models is not as easy, apparently. So there is a lot of complexity going on, and this complexity comes from different sources. So there are challenges related to just distribution of the training. As you go and scale your model up and up, you need to take care about how to split your model into chunks, how to distribute it across multiple devices, and that's not easy. On top of that, there is a lot of ML complexity, especially when we are talking about those multi-billion, 100 billion parameter models. It's a very large number of parameters. And even tiny errors in learning rates or numerics, they accumulate at that scale, and that frequently result in your model blowing up. You need to look into all of that, and when you try to reproduce models from the papers, quite frequently, the hyperparameters that has been used in that particular paper doesn't work that well for you. For example, because the batch size used in the paper is not very well fitted for your infrastructure, or the precision which they've used is not exactly written out, or you use slightly different libraries. So it's not easy. And when we are talking about really large-scale models, all of that experimentations, all of those mistakes are really expensive. And you kind of ride a lot, and there are a lot of stakes on getting that large run right. So how do we go about that, and how we can solve that? At Cerebras, one of our, I think, goals, or the only goal, is to make those large models more tractable. And we do that across multiple streams. So we build very large processors. We build the largest and fastest AI accelerators. We connect them into clusters, and one of the, I think, main advantages, which I will spend some time talking about, is we make them really easy to use. We train models. We release some of the models to the open source. We train multiple models to enterprise customers. We do that more and more frequently lately, because many customers come to us, and they're not asking just for a hardware, but they're telling, OK, we've heard this GenAI thing is happening. Can you help us use it for our problem? Can you train us a chatbot? So we are doing more and more of that. And because of that, we learn a lot, and we right now have quite extensive ML expertise in-house. So just really quickly, I mentioned we build very large processors. We are the only one who builds a wafer-scale processor. That's a processor of the size of the whole silicon wafer. That's the largest chip on Earth, literally. Has tons of transistors. Many of you probably don't care about number of transistors, but what it results in, you have much more compute on a single device, so a single accelerator can replace multiple of GPUs. You have much more memory, which helps us with the acceleration from sparsity. We package those processors into our systems. some time. I did not drink, so somewhere I can tell you tons of stories how challenging was it to actually power, cool down, and build everything that can enable programming and functioning of this humongous chip. So we have our own system designed for that. The system can be installed in a standard data center, and we package that with some other components. One very important component which we place together with our accelerators, with our systems, is the component which we call MemoryX. You can think about that as an off-chip memory which can scale completely independently from compute. What it means that I can attach from terabytes to petabytes of memory, which can be used to store all of your model parameters, model states, et cetera. I can attach it to a single accelerator, to 10 accelerators, to thousands of accelerators. So it gives me an ability to scale completely independently, compute and memory. And this is a very huge advantage for how we build those clusters. So we stack all of those components together and build large-scale clusters. But no matter how many nodes you have in a cluster, it always viewed and programmed as a single device. So across all of those clusters, all of their memory units are connected in a single, for the developer, you view that as a single pool of memory for your parameters. And you have a bunch of accelerators, and you distribute training using data parallel training only. So what that means that as an ML user, as a developer, I always program my cluster as a single device. My code, I never have to care about distributing the model and splitting the model. No matter if I use a single system, 10 systems, thousands of systems, the code I write is always for a single device. And my model, OK. And my model always fits. No matter if it's a billion parameters or trillion parameters, it always fits. And I can train that model on a single system or multiple systems. You can think that training a very large model on a single system is not that useful because it takes time. That's true, but it's very convenient for debugging. So whenever we start or plan to start a very large run on a large cluster, we always run first iterations on a single system without spending time on large clusters, and we figure out that everything is proper and correct, and then we launch large run on multiple systems. So let's come back to ML. So all of this hardware neat, right? So how can this help me with ML? How can I make sure that I get that model of the highest quality? I'm sorry, I'm not sure what's going on with this clicker thing. There are several things which you need to take care of when you train those models. First of all, obviously, careful data preparation and cleaning is important. But two last bullets are extremely important. The first thing, it's really important to select all of the model features and training approaches very carefully. And we do that where we have a very large number of small-scale experiments. We run hundreds, in some cases thousands of experiments at very small scale. And I'm talking about tens of millions, maybe hundreds of millions of parameters. And then we scale those learnings for large-scale models. And we plan all of our runs leveraging scaling laws, which enable us to predict the quality of the models at different scales. So I'm coming, maybe I can say from my accent, I'm originally from Russia. In Russia, we have a very nice saying, which can be translated literally, measure 7 times, count once, or English version of that, better safe than sorry. And I think that's a very nice saying for what happens with those large language models, or large models in general. Those GenAI models are really expensive and long to run. It takes weeks or months of time and thousands of GPUs, costs millions of dollars. So it's really important before you start that multi-million run that you get everything run correctly, because errors are really costly. So it's better to spend a little bit more time on small-scale experimentation, predict expected results so you can monitor your run, and make sure, run that long run with confidence. How can you do that? You iterate a lot at a smaller scale. So internally, we design experiments at small scale. Here on the slide, I have 500 million parameters, but literally, we start even at a smaller scale. We run tons of experiments, pick right hyperparameters. We use those small-scale experiments to predict the quality of larger-scale model, and we iterate. So we iterate, iterate, iterate until we have high confidence that that large run, that multi-10, multi-100 billion parameter run is going to get right. So this a little bit of experimentation will save you time at the end, but it also comes at some cost. And especially if you do that on GPUs, switching between this 10 million parameter run and 10 billion parameter run is not as simple, because pretty frequently you need to change your code. You need to decide how do I distribute my model across multiple devices. You don't have to do that on Cerebras. And that, I think, to me, as an ML researcher in the past, that's one of the main advantages of the whole thing. Because we literally run the same code, no matter the size of the model. You just change the size of the layers and the depth of the model. And we can change the size of the cluster. And it's really shortened the time of data experimentation. And I think that's the secret of high-quality model. So being able to run those small-scale experiments and being able to go from small model to large model, from small cluster to large cluster is one important thing. Another important thing is we want to be able to predict expected results. How do we do that? We leverage scaling laws. So I personally believe that scaling law is really important, and you shouldn't ever launch a very large run before you know what you can expect from that large run. What scaling law is? That's an empirical law, a power law, which shows you dependency between expected evaluation loss and amount of compute that you throw into the training. Amount of compute obviously depends on your model size, on the data set size. So typically, you will see a plot like this, where on the x-axis, you will have training flops, and on the y-axis, you will have test loss. And if you get everything right, you will have this logarithmic scale on x-axis, and you will have a line which shows you as I spend more and more compute, my evaluation loss goes down. So what we do, we run experiments at several scales, small scale, and then we fit the power law for a specific data set, for a specific model we are training, and we can predict how good we could expect that model to be if we scale that to, I think, 6 billion parameter, 13 billion, 20 billion, 100 billion parameter. And then when you run that 100 billion parameter run, you can see where you expect your run to be at that particular point. And if you see that you deviate from that scaling law, that's a flag, red flag for you. You need to go and check if your setup is right, if you did everything right. So it lets you to really monitor the run and predict ahead of time what kind of quality you can get out of the model. So we use scaling laws to, again, predict the run, budget the compute time, and always check whether the training run is on track. So this plot on the slide comes from the family of GPT models that we've trained last year, where we derived the scaling law for pile data set. You can check a paper and read more about that. Scaling laws are really great, but it's also not that simple to work with them, especially as you increase the scale, you increase the model size. There are certain complexities which require careful navigation. You need to think about how to optimize, how to set hyperparameters, optimizer hyperparameters, how to choose initialization, how to choose the batch size. You need to deal with all of that, of those things at scale, and being able to move between different scales at a relatively small scale, again, helps you to make sure that you get that scaling law right and you can predict everything in the future. One of the things that is really useful as you work with these scaling laws is what's called maximal update parameterization. So that's a way to first initialize your model and add some additional scalars within the model in such a way that the outputs of every layer, no matter how wide your layer is, have the same norm at the end. So that makes your hyperparameters much easier to transfer between different model scales. Literally, don't touch this thing. I'm not sure what's happening. So we've seen that with the maximal update parameterization, large-scale runs becomes much more stable and much more predictable. So here on the plot, I show the deviation of actual runs versus predicted loss versus the scaling law. The blue is with standard parameterization, orange with their maximal update. And if on the previous slide you see that those blue points are falling approximately on the line, in reality, if you zoom in, they're not exactly on the line. They're jumping back and forth. So with maximal update parameterization, that's much more precise, and the runs are much more stable. So if you are not trying to fine-tune your model from existing checkpoint, which doesn't use maximal update parameterization, you're starting something from scratch, really recommend to use maximal update parameterization. And also you can check either in original Microsoft publication or in our publication how to use this. So in summary, scaling laws studies help us to understand the training. They help us to choose model architectures, training algorithms, hyperparameters optimizers, and also it's a really useful tool to measure the dynamics of the training and to make sure that you are on track. And it gives you a formula for scaling up. So now whenever the customer comes to me and say, OK, if I pay you that much more and we train 60 billion parameters instead of 30 billion or 100 billion, how much better my model will be? Now we can answer that question, and it's really important. So we talked about, we used those scaling laws quite extensively. One of the work which we've published, a model trained with a Core 42. It's a bilingual model, Arabic-English. It's state-of-the-art model. And we use scaling laws to get to that state-of-the-art model quite extensively. Just to give you a sense of what it looks like, whenever we train a model, we plot tons of those lines. So when we started working on this JACE model, we get only access to the Arabic data set. And we wanted to train Arabic language model initially. By plotting those things, we pretty soon realized that we don't have enough data. No matter if we increase the size of the model, we can predict that there is no way for us to get a better model. So we need to increase the data. How can you do that? OK, let's see if we throw some English into that. We experimented a ton at small scale at different data mixes. So here I show just several ratios, like 1:2, English-Arabic mixture, 1:1, 2:1. But in reality, we've done multiple other exploration as well. We plotted all of those, and we studied from very small scale experiments what quality we could expect at a larger scale. So we realized that at a smaller scale, for example, if you add English into the model quality in Arabic degrades. Maybe unsurprisingly, the capacity of the model is not enough. But as you increase the parameter count, as in you increase the size of the model, you can see that adding English actually helps. So if you add English into your data set and your model is large enough, your model will become better in Arabic. And we used all of those insights to train this state-of-the-art model. And that model set new record for open source Arabic language models. We've just, a couple of months ago, finished the third phase of the training. And you can see it outperforms all kind of other models in Arabic at that scale. Another model, which is a testament to this approach of small-scale experimentation, a model also released last year, BTLM, trained together with OpenTensor. So the goal for this project was to train the best possible model at 3 billion scale. So when we released that model, it was state-of-the-art model, and you can see it was outperforming by quite large margin all other 3 billion parameter models available out there. It's by far the most popular 3 billion parameter model in Hugging Face with more than 1 million downloads. And again, how we got to that quality of the model with the many chip ablations. So we really run hundreds of experiments and 100 million scale. We studied every single change in the model. So what if I change my activation from Jello to Swigglue? What if I change my positional embedding? What if I change my some hyperparameters? So we've studied what improvement we can expect out of each of those things at small scale, and then we scale the model up. And that's the secret how you can get the best possible model out of this. So we talked about how small-scale experiments and scaling laws allows us to train the best possible model efficiently by using less compute. But we know that we can do, and actually we need to do better. If you look at the amount of compute that's needed to train those large models, that's insane. So we see that demand for the compute to train those models increased by 40,000 times in just 5 years. So this trajectory is unsustainable. And we believe that sparsity is a key to train those models cheaper and more efficiently. Why is that? Neural networks, many of them are sparse. So sparsity exists in some of the neural networks. If you use dropouts, if you use activations like ReLU, your activation is already sparse. You already have zeros in your models. But on top of that, neural networks can be made sparse. And it actually intuitively makes sense, because when you train your model, you have tons of parameters, and then at the end of the day, some of those parameters are more meaningful, some of them are less meaningful. So you can prune those which are not as meaningful. And as you prune them, you don't want them to contribute to the computational cost. But in order to take advantage of that, you need a special hardware. So sparsity acceleration, the ability to take advantage out of sparsity, is memory-bound problem. You need a lot of memory to be able to efficiently do computations on those sparse tensors. So for example, if you do just dense matrix-matrix multiplication, you need 1/1000th of a byte to be retrieved for every operation. And that can be achieved pretty well with existing GPUs, because you can reuse a lot of the data, and you can use those small caches at high reuse data to keep GPUs busy. But if you want to run operations with sparse tensors, you need 1,000 times more memory bandwidth, which is not available on any chip. And on Cerebras, one other kind of trade-off we made, in addition to making the chip very large, we allocated way more space on silicon to memory. So we have completely different compute-to-memory ratio. And this enables us to directly speed up from sparsity. And there is a lot of opportunity there. So we can accelerate, taking advantage from all forms of sparsity. So in this plot, there are just 3 examples. So we're talking about dynamic activation sparsity from things like ReLUs and dropouts. Google, for example, measured that if you use ReLUs in fully connected layers and LLMs, you can get those models 95% sparse, those layers. That means that amount of compute that required to train those models can be reduced by 1.7x. So you can train your models 1.7x faster if you have proper hardware. Mixture of experts is another example of sparsity. So if you choose just only 2 active experts out of 8, that means that in those fully connected layers, I'm 75% sparse. I'd like to be able to take advantage of that, and we can do this. And we also explore a lot unstructured sparsity. So we have our own technique we call sparse pre-training, dense fine-tuning. We've published a couple of papers on that, and that enables us to accelerate training even further. So we can speed up training by 2.8x compared to dense baselines. So all of that are tools we are still exploring. Many of them, some of them are used heavily, some of them are still to be kind of proven, but there is a lot of opportunity there. And I personally believe that that's the way to train large-scale models in the future. So we talked about mostly language models. But we know that there is a lot of modalities around us, images, and I just wanted to show you some of the recent models we've trained, which are multi-modal. Multi-modal emerged, have been emerging for a couple of years, but became really, how to say, took the world over, probably over the past few months. The amount of multimodal models released and amount of repositories which are out there which use multimodal models are blowing up. One thing, though, about that every one researcher puts his or her own multimodal model in his or her own repo. And if you want to experiment and take, OK, I would like to use this visual encoder and this language model and this training objective, it's not that easy to combine all of them. So one of the things we've done in Cerebras, we kind of built a very configurable code base to experiment with all of that. So we wanted to be able to plug and play with different backbones and different encoders. And with that, again, being able to experiment faster at different scales with different components, that's key to success. So pretty quickly, we were able to reproduce state-of-the-art results in just a few weeks. So here we're showing comparison against standard Lava models. So orange, Cerebras gray is state-of-the-art. So we've been matching state-of-the-art pretty quickly. But then by experimenting, again, at different scales, pretty quickly we also improved state-of-the-art. So we trained the model with 7 billion language backbone on a smaller resolution images, which outperformed Lava 1.5, which has been trained with a much larger language backbone and higher resolution images. So that was pretty exciting. And again, that took us quite a couple of weeks to get those results. And just to entertain you in the final few seconds of the talk, here are some of the examples of that model. So here you see that we're asking the model to tell what the coins are. By the way, for me, that's a very also personal example. I moved to States 10 years ago. My older kid was 5 years old. Got to the kindergarten, and she was bringing back homework and telling, Mom, can you help me solve this? And no way. I have no idea what those coins are. So if I had that model before, I would be much better off. And another example, my colleague actually folded this towel with the sunglasses trying to trick the model, and the model got it right. So that tells you that actually the model is capable to understand what's inside the image. It's not only about textual context, it actually understands what's in the image. So that's, I think, really exciting, and we are looking forward to see what else can we build out of these models. Many models that we train are available on Hugging Face. We release, and when we work with customers, we typically give discounts if they agree to open source the models we train with them. So come and check these checkpoints. We have also one data set released, working on some more. And kind of in summary, at Cerebras, we build specialized hardware. So we've started with very large chips, but more and more we're becoming more of a ML company rather than hardware company, because again, those customers coming and they're telling not sell us a chip, but build a chatbot for us. So we're doing all of that. Internally, we rely a lot on small-scale experiments and scaling laws. And I do believe that that's the secret to get high-quality model. And we are still exploring what I call special sorcery for us, sparsity, to accelerate training even further and to make training of those large models even more tractable. Thank you.